But what you find eventually is you can go as far back as you want, and you just introduce a new beta each time. So what you could see is, if you want, you could see the following. A sub big N sub k is less than, by the same argument, beta to the k of A sub n. So if you go any farther than big N, such as k more places, you can compare it to A sub n, beta to the k. And so what you have then is exactly what you need, namely the sum of the A sub n's. Let's see what we'll do here. Let's start at A sub n and look at the tail. So that's how we're using the Cauchy criterion again. K goes from 0 to infinity. This is just A sub n times a certain sum of beta to the k. But this thing converges. So this tail is bounded by A sub n sum beta to the k. And that's enough to give us convergence of our series. Sorry, that's A sub n, isn't it? Thank you. Okay. Great. Okay, and then what happens in the other case, for the divergence case? For divergence, we can see what the tails, the terms don't go to 0. Don't go to 0. Okay. Okay, so it's just very similar spirit. All right. So we've developed a lot of tests for series. One of the most important series that you encounter are power series. What is a power series? Well, a series is basically a sum of a bunch of numbers. A power series might involve variables. So if Cn is complex, possibly complex coefficients, a power series is something like this. Cn z to the n is a power series. So I'll think of this as maybe a constant plus C1 times z plus C2 times z squared plus dot, 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 and it goes on. N goes from 0 to infinity. This is a power series. Why do you think it's called a power series? It's a series of powers, okay, of z. Z here you think of some, basically a complex variable in z, a complex variable. Or real variable, I'm just keeping this general, okay. Okay, so here's a question you might ask. If I have I'm given a bunch of C's, right? So Leon gives me a bunch of C's like this, and I say, okay, well, for what values of Z does this series converge? That's a question. When does this series converge? So for what Z does it converge? There's a question. And the nice answer to that is, hey, you know what? We can use our knowledge of series convergence tests to answer the question. So here's a big theorem for series. If alpha is, no surprise here, let's look at the limb sup of the nth root of. Now, if I were to just apply this particular root test to the power series, what should I put in these absolute values there? Cn z to the n, yes? But if I put them in here, Cn z to the n, and I take the nth root, then you can see the z to the n and the nth root combine, yes? Would give me a z or something, right? And normally then I'd be comparing that ratio to 1. Yes? But that involved, there's a z involved there, yes? So if I ignore the dependence on z, let's call this thing alpha, and I just take the nth root of Cn, and then let r be 1 over alpha. There's the 1 that's making its appearance. Then the claim is the Cn z to the n converges if the absolute value of r, if the absolute value of z is less than r, and it diverges if the absolute value of z is bigger than r. And this r has a special name. It's called the radius of convergence. So some of you have seen this in other courses. The surprise is the set of all places where this series converges actually forms a disk. It's a circle in the plane. It's centered around 0 in this case. And it's amazing it's a circle. But you can see where it comes from because the proof involves the root test. And what you find is basically the sum of, the nth root of an, in this case, is z times the nth root of Cn, where an is Cn Zn, z to the n. And what you're hoping is that the lim sup of this is less than 1, right? So we stick in lim sup here. And I stick in a lim sup here. I'm hoping to compare this to 1. But wait, what's this part? This part is the thing I've defined to be, I've called this alpha here. And so really we're just looking at comparing z to 1 over alpha. That's where the r comes from. Okay, so this is the proof idea. I'm not going to carry out the proofs very carefully here because you can see it written carefully in your book. But the idea is what you should remember. We're just using the root test. Okay. Okay, power series. Yeah, that's great. Okay, more stuff is said about power series actually in Math 132. Okay, and also if you take Fourier, you do power series. If you could. You explore them more in other classes, so I won't say too much more about them here. Here's a question for you. Speaking of series, what if I have two series, two sequences, AN, BN, and I want to know something about how to combine them and study them? So here's a question. What can I say about the sum of AN, BN? Can I say something about the sum of AN, BN? There's a question. And the main excuse for trying to answer this question is to show you something I think is really neat. And the book doesn't actually, it does talk about this, but doesn't actually say why. It's called this, and that's the idea of summation by parts. So summation by parts, by parts should remind you of something. Like integration by parts. So let's see if you can figure out when I write this down how this